Hello, everyone. We are very happy to welcome David Sher this week, who's going to talk to us about nodal counts for the Dirichlet-to-Neumann operator. As usual, don't hesitate to unmute yourself during the talk to ask questions or even to ask them on the chat. We will tell them to David.
Perfect. Thank you. So I'd like to thank you, Laura. Thank you, Alexander and John, for the invitation to speak here. It's a lovely thing that you've been doing during the pandemic to get this started. So as Laura said, I'm going to be talking about nodal counts for the Dirichlet-to-Neumann operator, and everything I'm talking about today is joint work with Asma Hassannezhad, who's at the University of Bristol. She did not ask me to mention it, but she has a potential postdoctoral position available. So you should contact her with any questions you may have. Okay. All right. So the geometric setting we're going to be in throughout the day is, so we're going to take a bounded connected Lipschitz domain sitting inside a smooth Riemannian manifold. So, a planar domain is an obvious example. You can think of a domain in a surface. And the restriction, bounded just so it's compact and the closure is compact. You're not worrying about that. Connected, I mean, everything always works for disconnected. It's just more annoying to state things. And Lipschitz is obviously a fairly weak regularity assumption. So we're going to be considering not just the Laplace operator on the interior omega, but Schrodinger operator. So we're going to have a potential function, and all I'm going to do at the beginning is assume that that's an L infinity. So again, a fairly weak regularity assumption. And finally, let lambda be a real parameter. Those are weak assumptions. Often we're going to assume for various results that omega and or q are more regular than this most general setting. I'll try to be very clear about where those assumptions are coming in. Okay. So we're going to define the Dirichlet-to-Neumann operator associated not to the Laplacian, but to the Schrodinger operator delta plus q, the potential, minus lambda. So both q and lambda are in there. And yes, you can sort of absorb lambda into q at times, but it helps to have them separate for reasons that we're going to see related to Robin problems. Just helps to see things. So to define this Dirichlet-to-Neumann operator, we do the same thing we do in the potential free case. Given a function f in L2 on the boundary, we're going to solve the problem. We're going to solve the problem. What's the sign convention for the Laplacian, Michael? It has positive eigenvalues. Okay. So you solve the problem of extending u in a way that satisfies the Schrodinger equation in the interior, delta plus q minus lambda, u equals 0. And then you take the normal derivative of that extension, the normal derivative of that interior extension, and that is dq lambda of f. Okay, so it takes the Dirichlet data of this extension to the Neumann data of this extension. Now, of course, there's a minor lie here if lambda happens to be a Dirichlet eigenvalue of delta plus q, as then you don't have a unique solution. You can add copies of the eigenfunction. But if you project off the subspace consisting of the normal derivatives of those eigenfunctions, you can still define the operator perfectly well, even when you have a Dirichlet eigenvalue. Under these assumptions, which are again fairly weak, the operator does have a discrete real spectrum. It's self-adjoint. It's bounded below. It's not necessarily non-negative, of course, depending on lambda. But we're going to let sigma 1 be the smallest eigenvalue of this operator, sigma 2, etc. And the corresponding eigenfunctions are phi 1, phi 2, etc. Now, those eigenfunctions, of course, live on the boundary. So these are boundary objects. And as per usual, we often consider the extensions which satisfy the Schrodinger equation in the interior. So the things you're taking the normal derivatives of. This is just the usual distinction between Steklov eigenfunctions and Dirichlet-to-Neumann eigenfunctions. Specifically, if q and lambda are both 0, which is included in what we're doing. Then UK are the Steklov eigenfunctions, and phi k are their boundary restrictions, and those are the Dirichlet-to-Neumann eigenfunctions. Okay, so standard setup in some ways, Dirichlet-to-Neumann operator with potential. Note that the potential shows up in the impedance tomography applications that this problem is famous for. It's usually about recovering the potential from various information about DQ. What we're going to be considering today is the problem of nodal counts. And so I'm going to, throughout the talk, I'm going to let mk be the number of nodal domains for the boundary Dirichlet-to-Neumann eigenfunctions, and let nk be the number of nodal domains for the interior generalized Steklov eigenfunctions. And as always, nodal domains are just the number of connected components on which the sign of any eigenfunction is monotone. Okay. And the question is, well, okay, in this generality, what can we say about the nodal counts? I should note at this point that there's been an awful lot of work in recent years on the nodal problem. It has generally focused on estimating from above and or below the size of the nodal sets of these eigenfunctions, both phi k and uk. There was a series of papers beginning with the result of Belavat and Lin in 2014, continuing with work of Jiuyi Zhu on these estimates. Josef Polterovich Jantoth and I wrote a paper doing real analytic surfaces, and the goal in the nodal set business is usually to attack some version of Yau's conjecture, which is a conjectured sharp in order upper bound on the size of the nodal set and lower bound on the same size. The analog of Yau's conjecture for the Laplacian. So the work today is going to be a little different, and in fact, it's an area where much less is known. So in order to explain what we're doing, I do want to go back and talk about the basic result on nodal counts, which is, of course, the Courant nodal domain theorem. So just to keep the notation distinct, I'm letting little nk be the number of nodal domains for Laplace eigenfunctions, Dirichlet boundary conditions, planar domain. And the Courant nodal domain theorem, this is 1923, says that the number of nodal domains is at most the index of the eigenfunction. So nk is less than or equal to k. There are versions of this that hold for Neumann boundary conditions, for Raban boundary conditions. All of them have basically the same idea for a proof. I do want to talk about the proof because it's again going to come back. So the proof of the Courant nodal domain theorem is it takes advantage of the variational characterization. So suppose that you have more than k nodal domains for the kth eigenfunction. I'm just going to call the eigenfunction fk, and then nodal domains omega1 through omega sub nk. And what you do is you take k of those nodal domains, and you consider the cutoff. You cut off the eigenfunction to be only on each of those k nodal domains. And so you take your fk, and you take chi u1 fk, going through omega 1. Sorry, that's a typo. You just take the characteristic functions. So there are k of these, and therefore you can construct a linear combination of them, f, which is orthogonal to all the prior eigenfunctions. And then you use this as a test function in the Rayleigh quotient. We know that by the variational characterization, lambda k is the minimum among all f which are perpendicular to the first k minus 1 eigenfunctions of the integral of the gradient squared over the integral of the function squared. And moreover, that we have equality if and only if f is an eigenfunction. And in this case, by direct computation, we have equality. So therefore, our Frankenstein linear combination f has to be an eigenfunction. The problem is that f is identically 0 on the k plus first nodal domain. And that contradicts the unique continuation theorem for the Laplacian. So that's the proof of Courant. It's a straightforward test function argument. So Courant's theorem has, of course, been improved in many ways. And one of the most interesting improvements for our purposes is by Playl. So in the same setting with the Dirichlet-Laplacian on a planar domain, Playl investigated not an absolute maximum for nk, but the lim sup of nk over k. So Courant's theorem, of course, says that is at most 1, rather trivially. But Playl was able to prove that it's less than some particular geometric constant, which is a little less than 0.7. So the proof of Playl's theorem is just a little bit different. It still looks at the restrictions to nodal domains, but the idea is that, okay, the kth eigenvalue on the whole thing is the first eigenvalue on each nodal domain. And then uses Faber-Cron, so the first eigenvalue of each nodal domain is greater than or equal to the first eigenvalue of the ball of the same volume. And if you add everything up and use Weyl's law, this falls out. Okay? It has, this is obviously in a very specific setting, but it has been extended beyond the Dirichlet-Laplacian planar domain setting by Berard and Meyer in 1982, who proved the same thing on closed manifolds. And then more recently, there's a bunch of work on this by Bourgain and others. I don't mean to leave anybody out here. I will mention only that Courant and Lena proved it in 2016 for Neumann and Raman boundary conditions. Okay. All right, so that's the background for what's known about nodal counts of the Laplacian, a very, very abbreviated version. What about the Dirichlet-to-Neumann eigenfunctions? So now we're in the setting of our capital MK and NK. And of course, the case that people have considered the most is where Q and lambda are both 0. And so this is a result of Cutler and Sigillito in 1969, a while ago. They proved that you have the Courant nodal domain theorem, NK. These are for the interior eigenfunctions. That the number of nodal domains for the interior eigenfunctions is again at most k. And their proof is again a modification of the proof of the Courant nodal domain theorem. It uses the Rayleigh quotient for the Steklov problem, which is this. Instead of taking so your Rayleigh quotient, instead of integrating over the whole manifold, you integrate only over the denominator in the boundary. Excuse me, you'll integrate only over the boundary in the denominator. Word order, good thing. So again, you're taking the infimum over all functions on the boundary that are perpendicular to the previous k-1 eigenfunctions. You take you minimize the Dirichlet energy divided by the L2 norm on the boundary squared. So a key fact in this proof is that all nodal domains for Steklov eigenfunctions have to have non-trivial intersection with the boundary. And now this is actually very special to Q equals lambda equals 0 because the reason it's true is the maximum principle. If you have an eigenfunction, if you have a nodal domain in the interior, it's 0 on the entire boundary. And it's harmonic. So it's 0, and that can't happen by unique continuation. So all nodal domains for Steklov eigenfunctions intersect this boundary non-trivially. And what that lets us do is play the same game as Courant. We can construct a test function orthogonal to all the prior eigenfunctions, right? Because the orthogonality conditions are non-trivial. Okay. And then that test function, that linear combination, that Frankenstein thing, is an eigenfunction by using, if you use Green's identity, you see that it's an eigenfunction vanishing on an open set. That uses Green's identity and the fact that, so the bit of the nodal domain on the boundary, you know the boundary condition, you have the Steklov boundary condition, and then you use unique continuation for harmonic functions. Okay. So as I've said, this clearly only works in the case where Q and lambda are both 0. Okay. And so now I ask what's known for MK, the Dirichlet-to-Neumann eigenfunctions, and the answer is not a lot. there's this sort of bad bound by, no, it's not bad. I mean, it's the best that's known. It can't be bad. But Alessandrini and Magnanini proved that, again, if Q and lambda are both 0 and omega is a simply connected planar domain, then you can have at most 2K nodal domains, which is, you know, it's great, but it's also sort of off by a factor of 2 from what we suspect might be the best bound. If you are thinking, so you can generalize this to get bounds on surfaces. If you play some topological games, again, nodal domains having to intersect the boundary imposes some topological restrictions on what they can look like in the interior. Again, the kinds of bounds you get are not particularly sharp, or at least we don't suspect they're particularly sharp. Okay, so that's as far as we understand it, that's the state of the art to this point. So the question I think one would ask is, okay, well, does Courant hold? Is nk less than or equal to k? Is mk less than or equal to k? Even if we have non-zero potential and or parameter? And the answer, which is kind of fun, is no. Courant will not work. In fact, we can break them. We can show you that Courant doesn't work just by letting, you can even let Q be 0, or equivalent, excuse me, let Q be, Q be 0, or equivalently just let Q be a constant. You don't even need a fancy potential to do this. And the reason for this is there's actually a very elementary counterexample taking advantage of this idea of Steklov-Robin duality. Steklov-Robin duality. So consider the following problem here. I want to take a function which satisfies delta u equals lambda u in the interior, and for which the normal derivative is sigma times the Dirichlet value of the function on the boundary. If you look at this problem, you can think of it in 2 different ways. You can think of it as, if you fix sigma, then it's a Robin eigenvalue problem, and lambda is your spectral parameter. However, if you fix lambda, then it's a Steklov type problem with sigma as a spectral parameter. So this is a set of ideas that is originally due to Lenny Friedlander, I believe is here, in 1991, and then it's been extended and generalized by Mazzeo and others. I'll get to more citations in a few minutes on that. Note that Friedlander was proving some really cool interlacing inequalities for Dirichlet and Neumann eigenvalues on planar domains. Some of the generalizations don't quite get that far. So here's this picture that I stole wholeheartedly from my colleagues, Alexander Girard, Misha Karpukin, Michael Levitin, Yosef Polterovich, illustrating this duality for a disk. And this picture shows where you have eigenvalues and eigenfunctions in this 2-parameter problem. So it's essentially in lambda sigma space. Lambda has been replaced by mu because that was what they used and they didn't feel like changing it. If you go to the right, your Robin parameter is increasing. If you go up, your Steklov parameter is increasing. And so what that means is if you take a horizontal slice of this, that's fixing sigma and giving you a Robin problem. And so the intersections of a horizontal line with these curves are the Robin eigenvalues of a problem with fixed sigma. Conversely, if you take a vertical slice, you get the eigenvalues of a Steklov problem with fixed lambda. And these are exactly what you get for a disk. So this is the case omega is a disk, and here they are. Okay, so the Steklov spectrum is this vertical cross section. The eigenfunctions, I mean, there's nothing fancy about computing these. It's Bessel function stuff. You find these separation of variables, and let's think about what they look like. So the dotted lines, these are ground states, and each of them is going to have a fixed sign on the boundary. But the neighboring blue lines are going to be sine and cosine of theta, and they're going to have 2 nodal domains each. The gold lines are going to have 4 nodal domains each. The green lines, it appears, are going to have 6, and so on and so forth. And now all you have to do is pick the right lambda. So namely, if you fix it either just above one of the ground state vertical asymptotes or just below one of the other vertical asymptotes. So if I pick lambda, say, to equal 22, then what's the ground state of the Steklov problem? It's going to be that gold line. And that gold line has 4 nodal domains. So the ground state is one of the higher order eigenfunctions in the angular variable, and therefore you're not just going to have a single nodal domain. And that immediately breaks Courant, because in fact you can arrange M1 and N1 to be 2J for any J just by picking lambda appropriately for the disk. Okay, so it's totally hopeless to get a full Courant theorem in this generality. And it shouldn't be shocking, I guess, from this example. We're not claiming that this is revelatory. It's just, if you look at it, you're like, oh yeah, that can't work. Okay? So a sharp Courant type bound is impossible. So what we're going to do is prove an asymptotic Courant type bound. So this is, again, joint with Asma Hassannezhad. The preprints on the archive, I'm happy to direct people to it if you would like. So this is for MK. These are the boundary eigenfunctions. And we are forced to make the additional assumption that our potential is smooth and that our boundary is smooth here. We will talk about potentially getting rid of those at the end. We are forced to make this assumption by the techniques that we end up using. So again, phi k are going to be an orthonormal basis of eigenfunctions of the Dirichlet-to-Neumann operator with potential and with lambda. Then what we prove is that the lim sup as k goes to infinity of mk over k is at most 1. So mk can be greater than k, but not too much and not for too long. So it bounds the excess. Of course, the sup of mk over k is, as discussed earlier, is totally unbounded because m1 can be as big as you like. So this theorem is, to our knowledge, again, new, even if q and lambda are both 0. So even in the straight up Steklov or Dirichlet-to-Neumann, I guess, case, we think this is a new result. And the asymptotic statement, it looks like Playl's theorem. So in Playl's theorem, you had lim sup of nk over k is less than or equal to 0.69 blah blah. But here, the bound for the lim sup is just 1. We can't do better than 1. And in fact, if you take a disk with q and lambda equals 0, we all know what the Steklov eigenfunctions for the Dirichlet-to-Neumann eigenfunctions for that are. They're just the same as the Laplace eigenfunctions on the boundary. And so mk is either k or k minus 1, depending on whether k is even or odd. And therefore, it is 1. So that means that what we have is sharp. You can't do better than 1 in full generality, at least not without some further restrictions. Again, talk about some open problems at the end. We have some ideas in that direction. Okay, so that's our main result for MK. I'm calling it Theorem A just to distinguish it from the other result. We also get something on NK. And this is going to look a little different. For one, we don't have to restrict anything. Q can be an L infinity. The boundary can be Lipschitz. So in order to state this, we have to, so we have Q and lambda, can be anything. And we're going to let D be the number of Dirichlet eigenvalues of the Laplacian delta sub Q lambda, which notationally I've defined it to be delta plus Q minus lambda. So it's the number of non-positive Dirichlet eigenvalues of this of the Schrödinger operator. Then letting NK be the number of nodal domains of these extended Steklov type eigenfunctions as before. The theorem is that for all k and n, you don't have nk is less than or equal to k, but the excess is at most d. Nk is less than or equal to k plus d. So for one, this does generalize the previous result of Cutler and Sigillito, because their Q and lambda were 0, and therefore D is 0, all Dirichlet eigenvalues are positive. So it bounds the excess. It certainly implies the lim sup result. It's a little nicer, looks a little nicer. And I'll notice there's a fairly large class of planar domains, in which there's a fairly large class of domains in which D is 0. If Q isn't too big, you can't perturb, if you just perturb, if omega is a planar domain, the Dirichlet eigenvalue starts positive, right? And so even a small perturbation isn't going to make it negative. And so in some sense, for Q sufficiently small or sufficiently close to 0, you're going to have the actual Courant type result here. Okay, so now in the 20 minutes I have left, or 23 minutes, something like that, I want to say a little about the proofs because I think they're kind of fun. So Theorem A, start with this one. So I'm just going to assume that the potential and the eigenvalue are 0 because it's the same proof. I can give some indications as to what changes, but there's not much. So our fundamental strategy is, well, it's the same as the Courant proof. I'm going to take a basis of Dirichlet-to-Neumann eigenfunctions. I'm going to let omega 1 to omega mk be the nodal domains. Recall that mk is the nodal count, so this notation makes sense. So I'm going to, again, multiply each of my eigenfunctions by a cutoff function for each nodal domain. And I'll note that these are all actually in H1 of the boundary because the omega j are nodal domains, and so therefore it's 0. So you're not cutting it off in some discontinuous way. But the big problem for using the Courant approach is that took advantage of the Rayleigh quotients. And here, the Rayleigh quotient we're considering involves more than just these boundary eigenfunctions. It involves the interior. So the Rayleigh quotient for sigma k, despite the fact that sigma k is an eigenvalue of a boundary operator, the Rayleigh quotient here involves the interior. This says something about the Dirichlet-to-Neumann operator being non-local. The Rayleigh quotient involves more than just the boundary. It depends on the not just the intrinsic geometry of the boundary, but the extrinsic geometry of the surface, the boundary being embedded into the domain. And so, well, these cutoff things, eigenfunction times cutoff functions, we live on the boundary. You can't use them as test functions for the Rayleigh quotient. The Rayleigh quotient needs to know what's happening in the interior. So that's a bit of a problem. So our solution is just to extend off the boundary. And here we're taking advantage of the fact that Steklov eigenfunctions localize near the boundary, at least in the asymptotic sense. So what do I mean by that? I mean that take a basis of Steklov eigenfunctions on a domain omega. If you go look at a compact set K in the interior, compactly contained in the interior of omega, and you look at the Steklov eigenfunctions, they're going to flatten out real quick as K goes to infinity. In the setting of a planar domain with Q and lambda equals 0, they flatten out super polynomially, and by flatten out, I mean literally any CK norm flattens out as any CJ norm, I suppose, as K goes to infinity. That's actually I think the first I've seen of that observation was a paper of Hislop and Lutzer back in about 2000. It is, people have studied this kind of decay. How quickly do Steklov eigenfunctions decay? So I believe Galkowski and Toth proved a few years ago that if the boundary is real analytic, the decay in the interior is actually exponential in the eigenvalue parameter. And there are some indications that if the boundary is less good, say Lipschitz, then you might not get super polynomial decay at all. So this is an interesting problem. But for the purposes of this, we don't need perfection in terms of what the decay is. We sort of know what Steklov eigenfunctions have to look like. They have to be harmonic or satisfy delta plus Q minus lambda equals 0. And we're just going to extend by exponential decay into the interior and cut off somewhere. So how do we do this? We are going to use boundary normal coordinates. So I'm going to let x, y be boundary normal coordinates in a small neighborhood of the boundary. X is a coordinate on the boundary, and yes, you have to use different coordinate patches, of course, as with any manifold. But y is going to be the normal coordinate, basically the distance from the boundary. And yeah, so for boundary normal coordinates, you don't need the full smoothness, but you do need something. It needs to be more than Lipschitz. I'm going to let chi be some sort of cutoff function cutting off near 0. So it's 1 near 0, 0 bigger, etc. And I'm going to define these extended cutoff eigenfunctions. So in x, the boundary coordinate, we're taking phi k, the kth eigenfunction, times the cutoff on that nodal domain, which has the nice advantage of being continuous in x. That's good, because it's 0 on the boundary of a nodal domain, phi k is. And then I'm going to multiply by e to the minus sigma ky, which is sort of what we expect it to look like heuristically, and then cut it off in y. So I'm not going too far into the interior. I should note that if you just compute the Steklov eigenfunctions for, say, a half plane, you get e to the sigma k times ix minus y, basically. So this is actually exactly what Steklov eigenfunctions look like on a half plane. You can do similar computations for a disk. And so we're going to use these extended eigenfunctions as test functions for the Rayleigh quotient. Okay. And as with most Rayleigh quotient problems, at this point, it becomes basically a computation of what the Rayleigh quotient is. And the key lemma in all of this is that, so we're not going to be able to bound this Rayleigh quotient by sigma k, because that would imply a Courant theorem with a bound of 1, which we know can't happen. But we are going to be able to bound it by 1 plus epsilon sigma k for any epsilon and sufficiently small k. Of course, k depends on epsilon as usual. So this is, the left side is the Rayleigh quotient for this extended test function. The right side is 1 plus epsilon sigma k. And so once we have this, you have mk test functions, all of which are mutually orthogonal on the boundary because they literally have disjoint support. And so if you have mk test functions that are orthogonal, then sigma mk has to be at most whatever the value of the top value of the Rayleigh quotient is, and that's 1 plus epsilon sigma k. So this is an inequality between sigma mk and sigma k. But we know how these things grow, sigma mk and sigma k. We know how they grow by the Weyl law, and all you need is the leading term of that. By the Weyl law, mk is less than or equal to 1 plus epsilon times k. And that's exactly what we wanted to prove. That proves the lim sup statement. Okay, so it all reduces to proving this estimate. It all reduces to this estimate, and the proof of this estimate is not that bad. It's basically a direct computation. I'm going to obviously suppress all the lower order stuff. So we're going to estimate this numerator by dealing with y derivatives and x derivatives separately. Cross terms are small. Yeah, just under the rug. Sorry, I'm not gonna show you messy things. I don't believe in that in talks. They're morally unimportant. So what do the y derivatives of this test function do? Well, the test functions are that. So y derivatives, hi. Here, have an extra sigma k. So we get an extra sigma k. And then when you integrate over omega, you're integrating both in x and in y. Integrate over omega j and x, and then just 0 to, I don't care, 1 delta, whatever you want to call it in y, wherever the cutoff is. And you get this, and you can actually just do the y integral. And what you get is a bound of 1/2 sigma k. The 1/2 comes from the 2 in the exponent. 1/2 sigma k times the integral of phi k, the eigenfunction, over the domain sigma j, omega j. But that integral on the right-hand side is just the denominator of the Rayleigh quotient for this eigenfunction. And so, okay, the y derivatives contribute basically a 1/2 sigma k to this estimate in the lemma here. Okay, so that's what they do. Now, The x derivatives are a little more interesting. The x derivatives, okay, they basically give the gradient. You need to estimate the tangential gradient. These are tangential derivatives. So I'm denoting gradient sub x is just the gradient in only the x variables of the eigenfunction, and you need to estimate how big that is over a nodal domain. It's L2 norm over a nodal domain. You do have a 1/2 sigma k, again from the integration in the y variables that helps. But still, it's not totally obvious what the gradient of a Dirichlet-to-Neumann eigenfunction is over a nodal domain of one of those eigenfunctions. If it were a Laplace eigenfunction, you just use Green's theorem and say, okay, it's phi k delta phi k, which is phi k lambda k phi k, which is okay, fine. Here we can use Green's theorem again. It is 0 on the boundary, which is nice, of omega j, and so you get 1/2 sigma k times the integral of phi k times the Laplacian of phi k. Okay, well, it's totally not obvious what the Laplacian does to phi k. These are Dirichlet-to-Neumann eigenfunctions. Yeah, the square of the Dirichlet-to-Neumann operator is a lot like the Laplacian, but it's not the Laplacian. You can't just replace that with, you can't just, if it were d, if that were d squared, it would be great, because then you could just replace, then you just get a factor of sigma k squared and an extra, and then which turns into a 1/2. So if delta were just d squared, life would be really good, because d squared phi k is sigma k squared phi k, and then you'd get sigma k over 2, and you'd have the proof with no need for the plus epsilon. So, well, it's not, the Laplacian's not d squared, but it's close to d squared. Their difference, and this is where we're using the smoothness of Q and of the boundary. Their difference is a pseudo-differential operator of order 1. And that's true because the Laplacian is a pseudo-differential operator, well, indeed a differential operator of order 2. D is a pseudo-differential operator of order 1. So d squared is a pseudo-differential operator of order 2. But the Laplacian and d squared have the same principal symbol. And because of that, their difference is a pseudo-differential operator of order 1. So write that, plug it in. The d squared part, we know what to do with. And we're left with estimating phi k, the integral of phi k times b phi k. We don't know much about b, but we do know that it can't screw up eigenfunctions more than big O of sigma k. So we have d squared plus b. The d squared literally just turns into a sigma k squared. And I claim there's an O of sigma k here, that the b term can be handled. And the reason that's true is the Calderon-Viancourt theorem, basically. It's the idea that a pseudo-differential operator of order 0 is bounded from L2 to L2. So we're going to, you apply that to the pseudo-differential operator b times d inverse. So we're going to write b as b times d inverse times d. We know what d does to phi k. It brings down a sigma k. And b d inverse is a 0th order pseudo-differential operator. And so the integral of phi k, the inner product of phi k and b d inverse of phi k, we know b d inverse being a 0th order pseudo-differential operator is bounded L2 to L2. And so this inner product is bounded by the square of the L2 norm of phi k. And we get that. And that's the proof. You throw in a test function to make sure you're restricting to omega j. Okay. Characteristic function. Is there something in the chat?
Actually, there's a question in the chat.
Mm-hmm. Yeah, it says, speaking of pseudos, Daniel, thank you. Would you expect theorem A to hold for any pseudo which has the same principal symbol as the Dirichlet-to-Neumann operator? Okay. This part of it, certainly. Maybe some of the computations wouldn't. You need the Rayleigh quotient. And so if you have both a pseudo-differential operator with the same principal symbol as d to n and a Rayleigh quotient characterization of the eigenvalues, then yes, I would expect it to hold. This is fairly weak. Yeah.
Right. Your proof requires that, but there might be a different proof. I mean, of course, it would have to be a real operator, so you have real eigenfunctions.
Right.
But still, maybe it's true much more generally.
It may well be.
Okay.
Agreed. That's an interesting thing to consider.
Okay. Thanks.
Yep. But yes, it uses pseudo-differential operators, which is kind of, you know, a large tool, right? It's a rather big hammer, and it's a rather big hammer being used to deal with a problem that maybe has another solution, but it's the one we have right now. Okay. Okay. So now in the last 10 minutes or so, I'd like to talk about what's going on with Theorem B, which is entirely different, an entirely different proof.
Sorry, can you remind what is Theorem B?
Yes, absolutely. Theorem B is the statement that the number of nodal domains for the interior Steklov eigenfunctions, the U case, not the phi case. Now, these are nodal domains in omega and not just on the boundary. That is less than or equal to k plus d, where d is the number of non-positive Dirichlet eigenvalues of delta plus q minus omega. Okay. So the proof of this theorem actually, it would be substantially shorter than the proof of Theorem A if we didn't have to write down a couple of things that were probably well known but not written down. So we use the idea of Steklov-Robin duality. So as I said earlier, this is, you know, a sequence of ideas that, as I understand it, started with Friedlander in 91, Rafe Mazzeo 91 as well, and has been generalized in various ways by some people. I want to note that Arendt Mazzeo generalized it to manifolds, a couple of papers in 2007 and 2012. And then Arendt and Terrell, Kennedy, and Sauter proved in 2014 that you can add a potential, but they only wrote it on planar domains. But their proof basically works for manifolds as well. What's the point? The point of all this is, as I illustrated with that picture earlier, if you take the kth Steklov eigenfunction of the kth Steklov eigenfunction for the Dirichlet-to-Neumann operator with eigenvalue sigma is a Robin eigenfunction of delta plus q with eigenvalue lambda and Robin parameter sigma, right? So a Steklov eigenfunction is a Robin eigenfunction. And we have a Courant nodal, the Courant nodal domain theorem works perfectly nicely for Robin eigenfunctions. So the big question is, okay, which Robin eigenfunction is the kth Steklov eigenfunction? And let's take a look at this picture again. This picture, despite being for a disk, contains all the essential features of Steklov-Robin duality for a more general omega. And in particular, you're like, okay, well, how many? So let's count. Let's count what the kth Steklov eigenfunction, which Robin eigenfunction it is. So if you take the kth Steklov eigenfunction corresponding to, say, a negative mu or lambda, then that's just the kth Robin eigenfunction as well, right? Because the kth from the bottom is the same as the kth from the left. But now, and the same is true for sufficiently small positive lambda. But once you go over one of these vertical asymptotes, one of these bumps, your count is now off by 1, right? So if I were to take, say, 10, and I look for the third Steklov eigenfunction, that's going to be on the green line, and it's going to be the fourth Robin eigenfunction because that black line has disappeared. So the third Steklov eigenfunction is the fourth Robin eigenfunction. And every time you have one of these vertical asymptotes, every time one of these eigenvalues goes to 0, those asymptotes show up precisely at the Dirichlet eigenvalues of delta plus q. And so the defect in the count is precisely the number of Dirichlet eigenvalues that are less than lambda, which is the same as the number of non-positive eigenvalues when you incorporate lambda into the potential. And so what this says is that the kth Steklov eigenfunction is the k plus dth Robin eigenfunction. And that instantly proves Theorem B. The only technical complications in this proof are because the the full Steklov-Robin duality results that were needed had not explicitly been stated in the presence of both a potential and being on a manifold. But this is all essentially due to Arendt-Mazzeo on the one hand and Arendt-Tyrrell-Kennedy-Sauter on the other. We just went through and checked that, yes, everything in fact does work, restated a few things because it needed stating. But the idea is just this. Okay, so that's theorem B. In the few minutes I have left, I'd like to just formulate some open questions that Asma and I have been thinking about, and I'd be, we'd love to talk to anyone who has an idea about any of these. Okay, first, does the theorem A, the one that we prove with pseudos, hold for a less regular boundary and or a less regular potential? We both feel that, we're using pseudo-differential operators to get L2 bound, basically, essentially L2, essentially it's an H1 to L2 bound on the difference between the Laplacian and D squared. Is there a way to derive that bound that doesn't use pseudo-differential operators? Because the minute there is, you get theorem A without the regularity assumptions that we're required to make to use the pseudo-differential calculus. We think it should. We have played around with layer potentials as an approach to this point without success, but it feels like it should be there. The pseudo-differential, it's so strong, and we just shouldn't need that kind of continuity. So our bound in theorem A, mk over k, lim sup, was 1, and we showed that 1 is sharp in the case where you have just a disk. But a disk is kind of a special, because Steklov problem is really a boundary-centric problem, and you're really one dimension lower. Playl's theorem only holds for a dimension greater than 2 for the Laplacian. You can see why it fails with 1, very straightforwardly. It only holds for dimension greater than 2 with the Laplacian. So here, maybe we need to restrict the dimension of omega to be at least 3 to have a Playl type theorem. And the obstacle here is that we don't have Fabre-Cron. And that means you can't do the comparison quite as easily, and we haven't quite found a good replacement for that. Again, I would suspect the answer to this question to be yes, there is such a theorem. And I would guess that it had, my guess would be that it would have the same constant as Playl's constant, which has again been improved in various settings. Finally, is there a way to quantify that that little o of k in the statement? So the mk less than or equal to k plus little o of k is precisely the same as the lim sup statement we made. And can it be quantified? For nk, we can say, oh, well, it's o, little o of 1, right? Or it's big O of 1. It's just D. Can we find a way to quantify that and or to find a way to think about the excess, the cases in which mk are greater than or equal to k? Is there something we can do there? So I'd be curious to hear any thoughts that any of you may have. But otherwise, thank you for your time.
Thank you very much for the talk, David. Mm-hmm. We have time for questions, of course. So please unmute yourself or just start speaking. Or ask in the chat.
In the proof of theorem B, mm-hmm. I got lost a bit. The eigenfunctions that disappear into infinity, they kind of reappear, right? So they can upset the count. So your proof is really, it's at most k plus d's. It's not exactly guaranteed to be k plus d's.
No? That's a good point. Yes. No, you're right. You're right. I shouldn't have said exactly k plus d. It's at most the k plus d because, well, hold on. No, because if you're above a dotted line, you're also to the right of it. So it'll show up in both counts. It is exactly the k plus d. Right? It upsets your count, but it only upsets your count if you're looking above it.
Okay.
Above and to the right are the same thing, right? So if it's +1 to one count, it's +1 to another count, the other count as well.
Okay. Oh, I see.
Yeah.
Okay.
Okay, yes, thank you. That's a good question, though. It made me think for a second. Wouldn't affect the result, but...
Anyone else wants to ask a question?
Okay, so, thank you very much for your great talk. I'm wondering whether there's any known results for lower bounds.
For lower bounds for
Yeah.
the number of nodal domains.
Right.
Hmm.
Because for the given eigenfunctions, we want to basically, know as much as possible about the information about nodal domains, right? So
Right.
not only upper bounds, but the lower bound information would be also very useful.
I totally agree. I'll say that for a disk, or in general for any in any case where the dimension of omega is 2, MK is essentially exactly either 2k or 2k minus 1, k or k minus 1, depending on parity. And that's because the eigenfunctions in that case, if the boundary is connected, actually, I should put a caveat there. If the boundary is connected, and if you have a simply connected 2-dimensional omega, then with a smooth boundary, say, then the eigenfunctions are Steklov eigenfunctions very closely approximate trig functions on the boundary, and so you get both lower and upper bounds there. But in general, I have absolutely no idea. That's a great question. Thank you.
Thank you. Thank you.
David, maybe just say a little bit. So if you allow potentials to constants, then again, it's hard to get any meaningful lower bound because these black curves on this curve, they're constants along the boundary. So, well.
Right. So if you add potential, I guess, yeah, that makes it hard, right? So, you'd only be able to make some sort of asymptotic statement, right?
Yep. So
right. Okay. It's the same exceptional problem.
The same exceptional problem, yes.
Right.
I have a question. Can I?
Hi.
Yes, go ahead.
When I look to your proof of theorem B, at the end you use the standard Courant theorem. But can you use Playl there?
You're asking, could you use Playl instead?
Because you have this. Once you have the labeling K plus D, and then you use the standard Courant theorem.
Could we instead? You're asking, could we instead use Playl?
Yes. At this place.
Interesting. I mean, I think Playl works for Robin eigenfunctions, if I'm not mistaken. That would be the Courant-Lena 2016. I suppose that probably does get you a. Well, hold on. Yeah, the Robin eigenfunctions. So yeah, that probably does get you a better result, doesn't it? That's a great point.
Yeah.
Am I? But Playl. My colleague is Okay. No, the problem with Playl is that it's asymptotic. It's an asymptotic statement, right?
Yes.
It's not so. So
your D depends on K. Oh.
Yeah, that's the problem.
Okay.
Yeah, Playl's asymptotic. If you had if you had a sharper, Playl, maybe there's a weaker version of Playl with a weaker constant, but an actual bound rather than just something about the limb soup. Then if you have something better, yes, then that would be great. But yeah, D depends on K.
But if you have a bound relating D and K, maybe you.
Yes, but
okay.
But I don't know that the result exists, right?
Okay, thank you.
That's a great question, though.
A priori, you don't really know how the size of D with respect to K.
Well, I mean, maybe if you dig into the proof of Playl a lot, maybe you get something. But I'm not convinced that, not to my knowledge.
I'm wondering what's going to happen if you take a ball, just n-dimensional ball, as Laplacian with a very small potential. Just if the potential is 0, then for the Dirichlet-to-Neumann, you have all these symmetries. So you have kind of highly degenerate eigenvalues with high multiplicity. You perturb a little bit, then all this split. And as we know, when they split, you can have some interesting stuff. Just, for example, as far as the count, I mean, if you take the nodal domains, just with potentially zero, you just go spherical. You're going to get spherical harmonics, right? Now you're going to get a splitting, and then you might have something. As far as low bound, I'm talking about low bounds.
Lower bounds again.
Yeah, about low bounds. You can.
I mean, that certainly sounds interesting. I think, you know, the idea of taking a small perturbation Q is certainly something that the applied people on this problem have thought about a lot. We have not considered it, but it's a nice thought. Thank you.
Can I ask a question?
Yeah.
Yes, Misha.
Can you go over your problem one, open problem one? Once again, what do you exactly want to?
One, yes. Does theorem A hold for less regular boundary and or less regular potential? Because we wanted to use pseudo-differential calculus, we needed to use pseudo-differential calculus, and that requires that both the boundary be smooth and Q be smooth. There are some results on partial pseudo-differential calculi, but they're somewhat complicated. We didn't dig into it.
Can you specify the bound that you want?
We'd love to show that the limb sup. Oh, okay. Want to show that the limb sup of mk over k is less than or equal to 1.
No, I understand. I mean specifically for this place in the proof. Right?
Oh,
you wanted like
okay.
Z squared minus delta is bounded
yes.
by.
I would like to show that B here is bounded from H1 of omega j to L2 of omega j. And that's actually irritating because you don't have a lot of control over the geometry of omega j. And that's part of the problem here. The cutoff function, which doesn't cause a problem for L2 norms, does cause a problem for the H1 norms. Yeah. My colleague is, Asma is commenting that, yeah, we did try to use your paper with Alex, Michael, and Yosef, the Hormander type inequality, and it's very promising. It's just that there are commutator issues with the cutoff functions.
Okay.
Right. The problem is that you're trying to restrict to a nodal domain and also use this sort of bound.
That's why I'm asking. Yeah.
Yeah. No, your paper. We looked. We're still thinking about it. We certainly hope that something could work along those lines.
But it still requires C11, not Lipschitz.
Yeah, Lipschitz there's no chance this approach will work for Lipschitz. I mean, boundary normal coordinates don't work for Lipschitz, right? So, C2 would be lovely. It doesn't feel like it should require C infinity. It should be more robust than that, but proof? Not there yet.
C2 I don't think it should be that hard. I don't know. I haven't tried.
You don't think it should be that hard?
But if you go to C2, but I don't know. It's easy to say if you haven't tried.
Yeah.
You haven't tried, then everything is easy.
We have the same instinct. It feels like it should be true, right? And it feels like it shouldn't be that hard to prove, right? And then everything we've tried has run into some sort of dead end or another. This commutators thing is actually, it's a really cool dead end. I'd happily talk to you about it, Misha, if you want, but yeah, it is a dead end.
Thank you, David. Thank you, everyone, for the questions.
Yeah.
Anyone else wants to chime in?
Yeah. Back to Bernard's question. The D in your theorem 2 depends only on lambda and the potential Q.
Mm-hmm.
Right. So it doesn't change with K. So what Bernard is suggesting gives you Playl's result on the cheap, kind of for free. Because you just divide by K and then you use Playl and D as a function of K. It doesn't depend on K. So it's a constant with respect to K and then it just disappears. Take limb sup, of course.
Can I comment on this?
Yeah, Asma, I think that doesn't quite sound right, but Asma?
Yeah, so if I understand correctly, you're saying that the Playl for Robin, applying Playl for Robin problem, right?
Yes.
So here, I mean, the only Robin eigenvalue that we are interested in is the 0 one. So if 0, the index of 0 goes to infinity. So the Playl for Robin is nk of k Robin eigenfunction divided by k. So here, it very depends where 0 eigenvalue of Robin goes. If the index of 0 eigenvalue goes to infinity, then yes. And in some cases, yeah, we do have, but it's not, I mean, it's not general, it's not.
But why zeros? It's k plus.
Because of the duality. So for the Steklov, we put, so let's think of like the proper, like a Steklov. So we have 0, so we have sigma and lambda. So when we fix lambda, then we talk about this, lambda is fixed.
Right.
Yes, but so you write k plus d for Robin eigenfunction. So I don't understand the
problem. The problem is that Playl's result is only an asymptotic result in lambda, right? It tells you what happens as lambda goes to infinity. It's not an upper bound.
No, it's here it's k plus d, which tends to infinity. That's what I don't. It's a result about the k. It's a result about the number of nodal domains of the kth eigenfunction.
Right.
Yeah.
Your lambda is fixed here,
It is
right?
not referring to lambda.
Lambda, but lambda is.
It's just referring to the labeling.
Oh, the parameter that goes to infinity is sigma, right? So you need Playls in the Robin parameter sigma, whereas you have Playl in
because the Robin
lambda,
parameter keeps changing. So it's not a fixed parameter Robin things. So
right. Yeah, okay.
I don't. What you wrote is k plus d Robin eigenfunction. So
yeah, but they fix lambda the eigenvalue and change sigma the Robin parameter, and in this
you mean the Robin parameter depends on k?
The Robin parameter is the one increasing with k. Yes, lambda stays fixed.
So I agree, because in this case the result for Playl was the fixed Robin parameter.
Sigma, but
here sigma is sigma k.
Okay.
Okay.
Right.
Yeah. Thank you.
These pictures are great, and they cause confusion exactly like this. Thank you, Bernhard, Greg.
Thank you, everyone. Okay, one last time. Does anyone wants to say something or ask a question? If not, let's thank David again. Thank you very much, David, for the nice talk.
Thank you all.
And we will reconvene next week for a talk by Jean-Claude Cunin, who will speak about Schrödinger operators with complex potentials beyond the Laptev-Safronov conjecture. So see you next week. Have a great week. Until then, bye-bye.